Sandwich bus. It is also referred to as busways. Introduction. The synthesization of flexible and thin insulation material with good temperature withstand capability, Class B and above, led to the development of the sandwich bus. It has enabled low-voltage bus conductors to be pressed against each other with a thin insulating material between them, conducting heat across the insulation for efficient dissipation, and making the assembly extremely compact. Presently, sandwich bus construction is limited to low-voltage applications in AC and DC systems. There are low and medium voltage cast resin bus, where the thickness of the resin insulation is significant. The main advantage of the busway over bus duct are as follows. Extremely compact. The cross-sectional area, reduced to approximately 15% of the equivalent, bus duct. Low inductive reactance and hence low voltage drop. Have a minimum degree of protection of IP55. Lighter and hence low cost of the support structure and installation. Easy to install and maintain as the number of fixings per set of joints is minimal. Much higher fault withstand capability. Claimed to be as high as 200 kA. RMS and 450 kA peak. With less sail area, it is subjected to much lower wind loads and solar radiation. The design lends itself to standardization and can be sold in the retail market. Meets fire safety standards as there is no path for the smoke to travel through the busways. Ideally suited for high-rise buildings, with tap-offs at each floor for power distribution. For a similar rating, it is cheaper than a bus duct. Fully encapsulated, hence conductors are not susceptible to corrosion. No requirement of anti-condensation heaters and drain plugs. No necessity of hot air blowing or dehumidifier for ensuring the integrity of the insulation. Very low noise levels. Interface capacitance is a welcome feature. Aesthetic look. Because of the above advantages, busways have replaced bus ducts in most commercial establishments, high-rise buildings, and data centers, where space is at a premium and aesthetics an important criterion. Few installations may also be found in process industries and utilities. For an identical current rating, the cross-section of a conductor inside a busway will be less than that in a bus duct since the evacuation of heat is more efficient in busways. Consequently, the losses in the conductor of the busway will be higher than that in a bus duct. There is, however, a section of clients and consultants who have vehemently opposed the induction of busways in power plants, oil and petrochemical industries, mining, and process industries. Their apprehension is that busways are not as reliable as bus ducts in industrial applications, and they cite a significant number of joint failures. A well-designed and professionally installed busway is a reliable product. Description. Cross-section and heat evacuation from conductor. The typical cross-section of a three-phase and neutral busway are shown above. In the case of a busway, since all the conductors are pressed inside an enclosure without any air gap, the heat generated by the conductors is transferred to the enclosure by conduction. The enclosure, in turn, dissipates the heat into the ambient atmosphere by convection and radiation. Consequently, the temperature rise in the conductor and of the enclosure will depend upon the efficient heat dissipation by the enclosure. The enclosure is made of 4 sections. 2 of these sections are pressed against the stack of conductors, and the other 2 are located at the top and bottom and held with rivets. All the sections are either extruded if made of aluminium or formed from sheet steel. Most of the heat generated by the conductors are transferred to the side section by conduction. Only a minor quantum of the heat gets transferred directly from the conductors to the top and bottom section by conduction. Nevertheless, a part of the heat gets transferred to the top and bottom sections by conduction due to its being in contact with the side sections. It has been observed that the bulk of the heat generated by the conductor is transferred by conduction to the 2 side covers, parallel to the plane of the conductors, that press the conductor and hold them in position. The surface area of contact is large. Several manufacturers incorporate fins on the side covers to dissipate heat more efficiently by convection and radiation. Fins effectively increase the surface area of the enclosure. Busways in horizontal and vertical orientation. Heat transfer from the conductor by conduction to the top and bottom cover sheet that are perpendicular to the plane of the conductors is minimal and inefficient. Further, the surface area of contact is small. Consequently, the rating of the busway will depend upon the orientation of conductors after installation. A busway ampacity with conductors in vertical orientation will be higher than with conductor in horizontal orientation. This variation is much pronounced when the height to width of the stack of busways is large. For smaller ratings with a single stack, the variation may not be significant. When the busways are installed vertically, as in high-rise buildings, the conductor orientation does not have any bearing on the current rating. The manufacturers must confirm the rating of the busways when installed as rises in high-rise buildings. The tap-off current extraction at various floors does reduce the heat generation per unit length progressively, and that more than compensates for the loss of efficiency in heat dissipation by convection. It is also an accepted practice to install a single vertical riser of busway comprising different ratings, considering a progressive reduction of current as it moves to higher floors. Standardized reducers can join busways of different current ratings to cater to this need. Configuration. Busways are manufactured in several conductor configurations, 3 for triple pole to 6 for triple pole with 2 neutral and 1 earth, depending upon the system, and installed in 2 different conductor orientations, vertical and horizontal. It is the normal practice to have all the conductors of equal cross-sections. The neutral conductor size is the same as that of the phase conductor. Under certain circumstances, the neutral conductor size may be twice that of the phase conductors. A 2-pole DC busway normally has 4 conductors wrapped in a common enclosure, with 2 conductors adjacent to each other, forming 1 pole. Interlayer insulation need not be provided for the 2 conductors of the same pole. Busways configuration. If an enclosure is made of extruded aluminium, the enclosure itself can act as an earth conductor and will have an adequate cross-section to meet the requirement. In the majority of cases, an earth bus runs outside, clamped to the enclosure. In some cases, the specification calls for protective earth to run inside the enclosure. Often, the cross-section of the protective earth is the same as that of the phase conductor. Depending upon the design, this can be made thinner to meet the specification requirement. Stacking of busways in horizontal and vertical orientation. In several designs, the rating of a single stack is limited to 2000 amperes with a copper conductor and 1600 amperes with an aluminium conductor. For higher current rating, the busways are stacked, either one above the other or one beside the other, depending upon the orientation. The number of stacks in a configuration will depend upon the ampacity requirements. Conductor. The conductor in a busway is either copper or aluminium. The conductors are always flat, with large width to thickness ratio exceeding 10. The geometry of the conductor will have minimal skin effect. The proximity effect will tend to compensate for the skin effect. The material utilization is very efficient. Most of the manufacturers tend to standardize on a single thickness irrespective of the current rating of the busway. The width of the conductor in most of the cases is normally limited to 3 sizes. The popular dimension for the thickness is 6 mm, quarter inch. The popular dimensions for the width are 100 mm, 4 inches, 150 mm, 6 inches, and 200 mm, 8 inches. When the current rating exceeds that delivered by the maximum bar size, busways are manufactured in 2 or 3 separate stacks as detailed in the configuration. Conductors of each phase are connected in parallel at the ends. With such configurations, it is possible to design a busway suitable for a current rating of 6,300 amperes with copper conductors and 5,000 amperes with aluminium conductors. When there is more than one parallel path for the connection, it is difficult to imagine that each path will share the burden equally. It will be a combination of unequal resistance and the reactance of each path. The currents in each parallel path of the conductor of the same phase will neither be equal in magnitude nor be in phase. The scalar addition of the currents will be more than the vector addition. Consequently, the combined losses in the parallel paths will be more than the losses if each of the parallel paths had carried an equal magnitude of current in phase. It is preferable to have each parallel path suitable for withstanding the short time current for the specified duration. There are a few manufacturers who offer project-specific busway with a single conductor per phase, up to the maximum rating, with a conductor size of 300 mm, 12 inches width and 12 mm, half-inch, thick conductors. Such an arrangement may not be the most efficient method of utilizing the conductor material. Nevertheless, it is preferred for certain applications. The entire length of the conductor, copper or aluminium, is tin-plated before fabrication. Enclosure. Busway enclosures are made of either extruded aluminium or formed with galvanized sheet steel. The normal thickness of aluminium is 3 mm, 1/8 inch to 4 mm, 3/16 inch, and for steel, it is 1.6 mm, 1/16 inch. There have been designs with side extrusions of busway made of aluminium and the top and bottom plates of galvanized sheet steel. Busway with aluminium enclosures need not be provided with a separate earth bar, since in most of the cases, the equivalent cross-section more than meets the calculated requirements of earth conductor cross-section for the specified fault current. Aluminium enclosures generate fewer losses and act as a better electromagnetic shield. They also exhibit good resistance to corrosion. It is the normal practice to subject the enclosure to a protective coat of paint to enhance emissivity and surface protection. When installed outdoors, the paint must be ultraviolet rays resistant. Enclosures, when installed outdoors, are provided with sun and weather shield to protect them from solar radiation and the elements. The manufacturer must confirm the rating of the busways for outdoor application with sun or weather shield. Insulation. Most manufacturers have adopted epoxy coating or mylar wrapping as the primary insulation for the conductor. Some manufacturers adopt a combination of both. Mylar is a registered trade name for biaxially oriented polyethylene terephthalate (BOP) insulating material. It has good dielectric and mechanical properties. It can be wrapped around a conductor. Since the film is thin, it transfers the heat across the insulation efficiently. It is necessary to have 100% redundancy to ensure that a pinhole in the insulation strip does not compromise the integrity of the insulation. Epoxy can either be coated by electrostatic spray or fluidized bed dip or extruded over the conductor. Epoxy coats are marginally thicker than the mylar insulation. A mylar film can be introduced between the coated bars and earth to provide an additional factor of safety. The gradient of the temperature across the insulation should be kept to a minimum to evacuate the heat more efficiently, thereby increasing the current rating of the busways. Most manufacturers confirm a thermal class F, though class B should suffice for the insulation. Joints. The conductor joint in the run of the busways is a unique design feature. An insulated bolt runs through all the conductors of all phases of conductors located in a site joint assembly. Most of the joints have only one bolt. In a connection where there is more than one run, up to 3 runs, each run will have a bolt at the joint. Some manufacturers provide up to 3 bolts per joint when the width of the conductor is significantly large. There are 2 methods of joining the conductors of 2 adjacent sections. Site joints with fish plates. Site joints with hole and spade. Site joint with fish plates. In the most popular design, the conductors of the adjacent sections are aligned and fish plates make the connection. In this method, the current gets transferred through 2 mating surfaces. Conductor to fish plate and fish plate to conductor. Manufacturers prefer this method for the following reasons. It makes the manufacturing of conductor easier as the profile at either end will be identical. Installation of the site joint is easier since there is a gap between the 2 adjacent sections of busways. Site joint with hole and spade. In this design, the ends of the mating conductors are shaped differently. One end of the conductor has a hole while the other end is shaped like a spade. At the site, the spade end meshes with the hole end and the joint is made. In this arrangement, the current gets transferred through one mating surface. Conductor to conductor. The overlap is also significantly longer. It makes the manufacturing of conductor and its identification at the time of assembly a little difficult as the profile of the conductor at either end is not identical. Installation of the site joint is difficult since there is an overlap of conductors of adjacent sections. Site joint with leaf spring. In both the alternatives, it is possible to run the clamping bolts on either side of the conductor assembly, with leaf spring to provide the necessary contact pressure, instead of running the bolts through the conductors, which result in the reduction of the contact area. In a busway, the joint temperature is the hot spot and therefore the joint must be monitored for low contact resistance. The conductor joint bolt must be torqued to the desired value. To ensure the same, all busways manufacturers install a double-headed bolt at the joint. The bolt is tightened holding the top head till it gets sheared, an indication that the desired torque has been achieved. The joint is the most vulnerable location in the length of the busways, especially when it is installed outdoors. It not only has to cater to the expansion and contraction due to thermal cycling in the axial direction, it must also restrain movement, perpendicular to the axis of the busways due to wind loads. The joint must maintain its integrity during the life of the busway. Insulation at the joints is also very vulnerable. The section of the conductor from the point it emerges from the busway's enclosure to the point it contacts the site joint fishplate is air insulated with very critical clearance and creepage distance. Any dielectric stress at this location due to ingress of dust and moisture or surge voltage will result in the failure of insulation. At the joint, there are two ways to hold the site joint enclosure plate in position. Conductor joint bolts accessible from outside enclosure cover plates. This arrangement is ideally suited for indoor installations. Conductor joint bolts inaccessible from outside the enclosure cover plate. This arrangement is ideally suited for outdoor installations. Typical installation of indoor horizontal run of busways. Busways installed indoor are predominantly supported from roof by hanger rods and clamped to the base channel. The maximum span for the support is predetermined and locations are identified based on the site joints. Typical installation of indoor vertical riser in a high-rise building. Spring-loaded support ensure that the weight of the busways is shared equally by all the floors and caters to the thermal expansion. Thank you. Mr. Balachandran graduated with a bachelor's degree, B.Tech, in electrical engineering from the Indian Institute of Technology, Madras, India, in 1967, and obtained a master's degree, M.E., in power engineering from the Indian Institute of Science, Bangalore, India, in 1970. He is a Fellow of the Institution of Engineers, FIE-India, Fellow of Institution of Engineering Technology and Chartered Engineer, FIET-UK, and Life Senior Member of the Institution of Electrical and Electronics Engineers, IEEE-US. He was the founder-director of Power Gear Limited and Busbar Systems, India, Limited. He has worked in manufacturing industries in India and the UK and is currently an advisor. He has engineered several busbar systems that have been manufactured and installed in various countries, including isolated phase bus for the largest hydroelectric power plant, 26 by 800 megawatts, at the Three Gorges project in China. During his professional career, he has developed and tested a range of bus products and their accessories. His area of interest also includes switchgear, instrument transformers, and power system analysis. The book, An Introduction to Busbar Systems, authored by V. Balachandran, is case-bound, hardcover, size A4, 386 pages, printed on 100 GSM glossy paper. Copies of the book can be purchased with a requisition to Bala at busbarsystems.net. Black and white version of the book is for sale in India, Afghanistan, Bangladesh, Bhutan, Nepal, Pakistan, and Sri Lanka at a cost of 4,500 Indian rupees plus freight. Color version of the book is for sale in all other countries at a cost of US $126.00 plus freight.